Alright, hello guys, welcome to one of your tutorials on the oscilloscope. Okay, let's get started. What is an oscilloscope? Well, it's a electronic piece of kit used in every lab around the world. Okay, you cannot escape them, and they're used for measuring time varying waveforms. Okay, now then, when you encounter an oscilloscope, okay, you try and measure it. You're measuring not in direct numbers, okay, just like you would on a multimeter. You read the number directly off it. Okay, in terms of oscilloscopes, you're actually measuring something that's displayed graphically. Okay, in the form of waveforms, you will actually see a waveform. If it's a sine wave, you will see a sine wave. If it's a triangular wave, you will see a triangular wave, and they're what you have to measure. Okay, and the way in which you measure off an oscilloscope is exactly the same way how you'd measure off a normal graph. Okay, if you have a graph showing you a sine wave, okay, you have the y-axis, which is the voltage, you've got the x-axis, which is the time. Okay, you'd measure it off much the same way. Now then, what I've got on my desk here are a couple of oscilloscopes. Okay, we've got a nice Agilent 100 MHz oscilloscope there, digital oscilloscope. We have a Hitachi Analogue oscilloscope. Okay, this is you still encounter these in the workplace probably. They're still commonly used, not as much nowadays since the advent of digital. But, yeah, that's exactly what we'll be teaching you how to use on this tutorial, as well as this one up here, which is a Tektronix digital oscilloscope. These are ones that you use in the lab. But before we get on and I'll show you how to use that one, I'll run you through this one. Okay, and hopefully after working out how to do things in the analog world which we live in, we'll do exactly the same thing on the digital one, and it will make a hell of a lot more sense. Okay, so they're your oscilloscopes. Okay, like I said, that's what we teach you on, and once you get to use the analog one, and we'll move on to the digital one, you'll get an appreciation of the differences between the two, and where some of the functions come from on the digital one, and how it relates to the analog one, how the analog relates to digital, and so forth. Right, so let's start off with a little bit of graphing. Okay, like I said, based on graphs. Everyone's done graphs. You did graphs before you even went to college. Before you came here, everyone should know what a graph is. So let's start off with that. Pretty whiteboard. Okay. So what do we have? We got our axes. Okay. Time, voltage. And let's whack on there a sine wave. So on a graph, sine wave, 0 is in the centre, and normally we have linear steps, okay, in the positive, linear steps in the negative, and same for a nice time period. Okay, there we have it. And if we have, say, 1 millisecond increments, so let's say milliseconds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 milliseconds time. Read it directly off, easy. Same for the voltage. Let's say take it in 1 volt steps, so it's a bit 1 volt, 2, 3, 4 volts in the negative, 1, 2, 3, minus, plus 4 volts. Simple. Okay, so it is 4 volts amplitude, 4 volts, what we call trough. Okay, because it's going negative, 4 volts amplitude, that's positive above 0. And from the peak to peak, add them together, 8 volts. So we have 8 volts peak to peak, and a period of 13 milliseconds. Done. And that's exactly how you measure it from one of these oscilloscopes. Now, on this graph, like I said, we've got linear intervals. On an oscilloscope, we have a nice knob called volts per divisions. Okay. Each of these divisions is 1 volt, so on the oscilloscope this would have been set to 1 volt per division. Time, these are all in milliseconds. Okay, each division is represented by 1 millisecond. So each one of these is 1 millisecond. Each one of these was 1 volt. Okay, so this on a knob on the oscilloscope, there is a knob with time written on it. Okay, so there's another knob over here with seconds per division, or sometimes it's referred to as the time base. Okay, and it would be represented as 1 millisecond. Now then, simple. Okay, division is 1 millisecond. Divisions for voltage, volts. It is 8 volts peak to peak times whatever. 1 over the time, 1 over 13 gives you the frequency. How to measure a signal. Simple. Now then, let's apply that to the oscilloscope. Okay, then here we have analog oscilloscope. Okay, and let's get started on this. First of all, power on. Okay, just to introduce you to the front panel, we have got time per division up the top here. We have volts per division knobs here, and the reason why we have 2 volts per division knobs is because we have 2 inputs. Okay, you can actually measure 2 waveforms at the same time on this oscilloscope. Right then, we have coupling for channel 1, coupling for channel 2. Little knob for telling us what mode we're going to use, so you can either measure channel 1, channel 2, or we can add them together, or we can look at them at the same time. Up here we've got our time, which I've already said, we've got our time position, and over here we have our triggering functions. I'll get onto triggering in a moment after I've covered the basics on here, because triggering is always a little bit of a problem area. Okay, it's not as simple as using the other controls, and it always causes a lot of headaches, especially if you're a first time user. Now then, whenever you use an oscilloscope first, okay, pay attention to the coupling. Okay, the type of coupling that you use is dependent on the type of signal that you're inputting. Okay, if it's a analog signal, an AC waveform, a sine wave, such. Okay, you can either have it set to the DC or to the AC. Okay, it doesn't really matter. What really does matter is if you have any DC component, or if your sine wave has any DC components in it. Okay, so if it's a DC, it's a straight line, make sure that it's switched to DC. If it's a sine wave with a DC offset, okay, your sine wave no longer oscillates around 0, it actually oscillates, say, around 1 volt, okay, or minus 1 volt, for example. Okay, then you would have to switch it to DC because it's got that offset on there. If you had that switch to AC, you'd remove it, the scope tries to remove out the DC components and tries to recenter the waveform around 0. So if you had a nice flat DC signal that you input on here and it was on AC, all that you would see is 0 volts. If it's AC and you had a DC component in it, all that you would see is the AC, and your sine wave will be oscillating around 0. You wouldn't get to see that DC. So first things first, whenever you switch on your scope, always make sure that you've got these set to ground, GND. Okay, and that allows us to use the position controls to actually position where our waveform 0 is going to be. So okay, ground is 0. Wherever our line is, that's going to be 0. So let's say for channel 1, so we've got our control here set to channel 1. Channel 1 is set to 0 around the centre of the screen. Change it to channel 2, and we can move our channel 2 up and down until it's more or less in the centre of the screen. And there we have it. And that's our first little setup done. Next, set your time and your voltage. Okay. For me personally, I normally set these to a value of 1. Why 1? Because 1's easy to work with. 1 multiplied by anything is itself, okay? 1 multiplied by 2 is 2. Easy. So, set your volts per division to 1 volt per division for channel 1 and channel 2. Now these are already set to 1 volt per division. My little knob is pointed to 1. And the same for time. I've set this one to 1 millisecond per division. Okay, you can't go to 1 second because it doesn't go that low. Okay, same for microseconds. Now you can change these. These are your linear increments, if you like, just like what we have on the graph, your steps that your graph goes in. These are your steps. So if this is set to 1 volt per division, each one of these divisions going up, going vertically, is 1 volt. So 1, 2, 3, 4 volts it can swing negatively, and 1, 2, 3, 4 volts it can go positive. Same thing with the milliseconds. Okay, starts on this side of the oscilloscope, and it's 1 millisecond per division going right away across the oscilloscope. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Can measure up the signal up to 10 milliseconds. Okay, so if the signal has a period of less than 10 milliseconds, I would see the cycles on the screen. If it's got a period of 10 milliseconds, I'd see just 1 cycle on the screen. So on. It's pretty simple. Okay, over here we've got trigger. Okay, now triggering is all about stabilising your waveform. It's a bit like synchronising it. Just like on the graph on the whiteboard, my little whiteboard. Okay, our sine wave started at 0 volts at 0 time. Well, 0 time doesn't exist, okay, in the real world. This is running in real time, okay. So, sine wave, if we had a sine wave on here, would be continuously scrolling across the screen because it's continuously changing in time, okay. At no point in time is the voltage ever consistent. It's continuously moving up and down, up and down, up and down. That sine wave is, okay. And the only way to really see a stable waveform on the screen to stop it from scrolling across the screen, moving in time, and that's to trigger. Okay, and trigger actually tells it the start point of the waveform. Now they're the basic controls. Okay, let's take our BNC cable. Okay, this is actually attached to a signal generator that I've got behind the oscilloscope here. Okay, so I'm going to plug in a waveform, and we'll see what it looks like on the screen at the moment, and set up the oscilloscope so we can actually view it. Okay, it's an unknown value. I'm not bothering to look at my signal generator. Let's plug it in and see what we get. Okay, so connect my BNC cable to the input of the oscilloscope on channel 1. Now then, at the moment it's set to ground, so all I'm seeing is ground. So let's change it to, say, AC coupled. And I can't see absolutely any change. Why not? Right, well, let's change our volts per division. No, still the same. Let's change that back to 1. Let's change the time then. Can we see any cycles? No, we can't. So, what do we do? Well, what could be the problem? let's go through the controls. Let's see. Right, well, our time didn't do anything. Our voltage per division didn't do it. Have we actually got our oscilloscope viewing channel 1? Like I said, we can view 2 channels at the same time or independently. Our mode is currently set to channel 2, so we're actually currently looking at this one over here. We switch it to channel 1. There we have our sine wave, or part of our sine wave. Now then, first thing that we do, we can see our positives on this side, so let's change our time so we can actually see some waves on the screen. There we go, we can see a full wave on the screen. Okay, now on an oscilloscope it's always best to view the signal as big as possible. Okay, so it means fiddling about with your controls, your volts per division and your time per division, just like measuring on a graph. Okay, the larger your graph, okay, the more increments that you can put on your graph. That means the more accurately you can measure your trace on your graph. It's exactly the same thing with an oscilloscope screen. Okay, at the moment our graph is going from bottom of screen, top of screen, 1 volt per division. So you can go plus or minus 4 volts, 8 volts in total, but we're only taking up really 2 divisions. Okay, so what we can do is we can increase our volts per division. It may seem strange that I'm increasing, but I'm actually decreasing to half a volt per division, or 0.2 volts. 0.2 volts, it goes off the screen. 0.5 volts per division, it's actually on the screen, so that's as large a signal as we can get on the screen. Same for time. Got quite a few cycles on the screen, but I only need 1 cycle. Go the opposite way, it's off the screen, so somewhere around there is quite nice. Right then, so let's do some measurements. Just like I said before, we've got triggering over here. Now if our signal wasn't triggered, this is what you would see. It's actually, your sine wave is scrolling across the screen because it's a continuous wave. Okay, it's continuously moving in time across the screen. It started at this point, it's just shot straight past, and it's somewhere in the past now. So what you need to do is you need to, because it's a continuous wave, it's always starting and stopping at the same point, it's repetitive. What you can do is you can trigger by turning our trigger knob. Okay, so it's the waveform stabilizes, and you can tell it to trigger at the center of the sine wave, so it actually starts at 0 just like a normal sine wave does, stops at this point, starts again, it goes off the screen slightly, and then it's back to the beginning and it starts sweeping again. This is actually still moving in time. If I actually change my time division to back to the dot, you can actually see it's actually still moving in time, so it's sweeping up and down. It's moving in time, even though it does look like that it's nice and stable on the screen. Now then, measuring this exactly the same way as we measure on the graph, except we don't have any numbers on our axes. Okay, so you need to do a little bit of maths, very simple maths, addition, multiplication. Nothing particularly complicated. You might want your calculator to do the time, because that can be a little bit of a pain in the arse sometimes. Voltages, same thing. Okay, so what do we have? We've got 2 volts. We've got, not 2 volts, sorry. We've got 2 divisions. Okay, so from the centre to the top peak is amplitude, and it's 0.5 volts per division, so this is 0.5. 1 volt. 1 volt amplitude, and the same thing negatively, 2 divisions, 0.5, so it's 2 divisions multiplied by 0.5, it's 1 volt going negative. 1 volt positive, 1 volt negative, we've got a peak to peak of 2 volts. Okay, you don't have to do it in halves, you can do 1, 2, 3, 4 multiplied by 0.5 volts. Again, 2 volts. We have 1 volt negative, 1 volt positive, 2 volts. Did I say that? Can't remember now. Right then, so we've got that's how you measure your voltage. 1 cycle, peak to peak, 2 volts, because it's half a volt per per each division. Now each of these divisions are broken up into points of a division as well on these oscilloscope screens. So if your signal just so happened to end up halfway in between a division, you can actually say, right, well, this is 1 point, and these is split up into 5, so it'll be one division, say, and a couple of increments more multiplied by time base. It's not difficult to work out. There's 5 divisions in each one, so it'll be, if it was halfway in between, it'll be 1.5 divisions, because it's half a division multiplied by the voltage gives you a value. Okay, we'll look at that later on, measuring it a little bit more accurately. Time is set to 0.5 milliseconds per division. So we have 1, 2, 3, 4, 5, 6 divisions. So it'll be 6 multiplied by the time base, which is 0.5. That gives us a grand total of 3 milliseconds per division period. From here, I've got 0.5, 1 millisecond, 1.5, 2 milliseconds, 2.5, 3 milliseconds. So it's just a time base multiplied by the divisions, exactly the same way as we do it for voltage. There's nothing real difficult about that. If you want to work out as a frequency, then it's just 1 divided by the time period. And in this case, it would be on here 333 Hertz. Job done. Now then, what happens if this was set to DC? Okay, this is with AC, so we're kicking out any DC in here. As you can see, it's quite even. Okay, it's oscillating around 0. It's going negatively as much as it's going positively. Now it's set to DC. Right, as you can see, DC coupled, it's actually got a DC component. It's shifting the waveform down. So, centre of our waveform is here. Ground was here. So it's actually moving it down by 1, 2 divisions. So you've got 1 division, 2 divisions. 2 times 0.5. So we've got a -1 volt DC offset. Okay, it's actually shifted it down. And that's the beauty of this coupling thing. Because we set it originally to ground, we know where ground is. When you switch it to DC, you know that it's gone negative because it's on the bottom half of the screen. Simple. But the peak-to-peak value is still the same. Still 2 volts peak to peak. Okay, that's 2 volts peak to peak with a -1 volt offset. Done. Period hasn't changed. Okay, voltage doesn't change. Time stays the same. And that is how you measure on a analog oscilloscope. And like I said before, you can have both waveforms displayed. So you've still got channel 2 here, and this is channel 1. And if we move this over to channel 2, we DC couple this. Okay, now then, because we moved over to channel 2, you have to make sure that your trigger is set to channel 2. That's just below the mode. Okay, so you've got channel 2 here. Next one down, there's channel 2, and it's triggered because it already had set up to trigger. It looks like it's a smaller waveform. Okay, but that's only because we've actually got this set to 1 volt per division. We set this to 0.5 volt per division. There we go. It's exactly the same what we had before. Okay, there's nothing to it. It's not rocket science. It just takes practice, and the more you practice, the more you use these, the easier it gets. So we can say ta-ta to our analog scope, and we'll move on to our digital oscilloscope. Okay then, here we have on our desk our digital oscilloscope. This is the one that you need to get familiar with, because it's the one that's on every bench in the lab. 2 different versions. This is version B. There's also version C on the benches, but there's virtually no change between the two. The only difference is version C can measure phase, version B can't. and version C has a extra couple of meg to play about with. Okay, but apart from that, all the controls are the same. You drive it exactly the same, and all the controls are all in the same place. So let's, while we switch this on, power switch is at the top on this one, hit on the way. While it's booting up, it takes a few seconds. We'll run through what we've got on the front panel here. Now we've got channel 1 input, channel 2 input, volts per division for channel 1, volts per division for channel 2, position again, just like on the analog one, horizontal position, and seconds per division. All the controls are the same, and not only that, we also have our trigger, it's down the side here, and our trigger level, okay, which you need to trigger the scope with. All these buttons across the top, okay, you've got some useful ones and some completely non-useful ones. Now you may have noticed already, you have two buttons called auto set and auto range. Personally, I think that those are pants and should be removed from the oscilloscope. If anything, it teaches you how to be lazy, and it teaches you how not to drive an oscilloscope. Okay, because you get so used to pressing the auto set buttons that when you get into any trouble with the oscilloscope, you won't have a clue how to use it. Okay, and you'll end up pressing buttons, twisting knobs till you go absolutely mad, and still what you have displayed on the screen will be completely useless to you. So don't get used to pressing those buttons, they're more trouble than they're worth. Now then, whenever you switch the oscilloscope on and it's all powered up, the first button to press is default setup. Okay, hit that button, it will go back to its factory settings. Okay, so if anyone's messed about with their time basis, volts per division, triggering, whether they've used any measure functions, cursors, whether they've changed the way how the oscilloscope acquires the images or displays the images, so forth. Okay, if anyone's messed about with any of those, it can make life a hell of a lot harder trying to reset up the oscilloscope. So unlike the analog one, we had to twist loads of knobs about in order to get it into some sort of default setup. This one is just a single hit of the button and it goes back to the default settings, which are stored in memory. Easy. Okay, so that's one of the things that makes life easier. After it's hit default, it'll tell you down here that it's actually set up, ready to use, and you can hit, say, channel 1. Right then, on the oscilloscope screen, if we go to channel 1, it displays our channel 1 settings. Okay, volts per division knob. There's no numbers around our volts per division anymore. That's because it's actually on a menu on the front display. Down in the corner here we have channel 1, and our volts at the moment is set to 1 volt per division. Our coupling is set to at the moment DC, so you might want to change that to ground. Our time base is now in the more or less in the centre of the screen. It's currently set to 500 microseconds per division. You might want to change that, you might not want to change that. It's perfectly fine. Okay, the only thing that we need to worry about is our vertical position. Default setup sets it to the centre of the screen, but you may want to move it to the bottom, you may want to move it up if you're displaying two waveforms, or you may want to keep life simple, just keep it in the middle. Horizontal position is where our waveform starts. Now, on a digital oscilloscope, because it's chock full of memory, you can read waveforms that happened in the past, waveforms that are currently happening, okay, and it stores those in memory for a time. So whenever you go into default setup, you actually can see it's travelling. This is the arrow at the top where our start of the waveform is going to be. Okay, so it actually starts a waveform down the centre of the screen. Okay, so it continues running that across, and then it comes back to here, and it continues back to where it starts. Bit silly. Let's move this to the front of the screen. Okay, and you can see our little arrow up here. It's at the beginning of the screen now. And to make life even easier, over here we've got our trigger level. Now, down on the menu it tells us what channel we're triggering on. So channel 1 is what we're going to trigger. So channel 1's the waveform that we're going to stabilise, whatever's plugged into here. And we have an arrow on the screen on the right hand side that corresponds to our trigger level. So instead of having on the analog one had to guess where the trigger was, okay, you had to move it very, very slowly until your waveform was stable, and then slowly tweak it till it got to the beginning of the wave, where it's in the centre of our sine wave, point of no change. Okay, on this case you can actually see where the trigger level is. It's got a nice arrow next to it, and not only that, it gives you the actual voltage of the trigger, which is quite nice. Makes life a hell of a lot easier. So you can just flick the knob and there you go, presto, it will be in the sine wave because you can actually see it within the voltage of a sine wave. Couple of extra things down here. We've got bandwidth limiting. Okay, you can either have it bandwidth limit on to 20 meg or off at 60 meg. This actually increases the resolution of the oscilloscope, so you can actually change it to a 20 meg oscilloscope essentially. Okay, and you have a much higher resolution, so it will use the rest of the value, your extra 40 meg bandwidth, okay, and it will compress it all down into the 20 meg, so you get a much clearer signal. And also, if you've got a particularly high frequency noises and whatever, you can actually switch that on. Anything above 20 meg as opposed to anything above 60 meg gets attenuated out, so you can actually clean up your signal as well. But normally leave bandwidth limiting off. Within the lab, within your first year or two of your degree here, just have it off. It's not really going to make that much difference to what you're going to be doing. Further down we have our volts per division setting. Now this can be either set to course, so as you move the volts per division, okay, it goes in steps of say 5 volts, 2 volts, 1 volt, half a volt, just like the analog oscilloscope, but you can also change it to do fine, so you can have points of your millivolts or points of volts. Generally keep it to course because we like to keep things simple, and if we drive it exactly the same way as our old analog one, we don't even have to change this one, just keep it on course, and we can work out voltage values and our time values, etc., exactly the same way as how we did before. Invert if you want to flip the waveform up or down. That's interesting one if you want to do any mathematical functions. Normally that's switched off because what you input is what you want to see. You only really switch that on if you want to start to do any subtracting of waveforms between channel 1 and channel 2. So keep that switched off. And most important one that always causes problems are probes. Now before I continue on with actually taking any measurements and showing how to measure on a digital oscilloscope, I'm just going to speak to you a little bit about probes. Now probes are what we do all our measurements with, okay, and I'm going to whack down on the bench in front of the camera here some probes. Now we've got our bog standard probe, you may have seen these, okay, we've got big chunky 4mm plugs which just go straight to a BNC connector. Okay, now then, the positive red is what we do all our measurements with, and this black one, okay, is ground. Okay, now it's not actually negative or anything like that, but as soon as you plug in BNC cable, that becomes ground. Okay, it's not actually, this end of the cable isn't connected to anything. Okay, I'm just holding it in the air, but it is an actual ground potential because it's connected back here now to the outer ring, the outer BNC connector. Okay, the outer shield. This is actually ground. Okay, if you take a look on the oscilloscope, it actually shows you a little picture of your socket. Okay, so the outer shell, the chassis of the BNC, is actually connected to ground, so that's a ground potential. Be very careful when you're probing circuits with oscilloscopes and probes, because anything that you connect to an oscilloscope, on one side of your probe will always be ground. So it's no good measuring say a differential voltage, but that should actually ground out one half your differential signal. Right. that's a normal probe. That's what we call a ×1 probe. Now, that's a normal coaxial cable, okay? It's just a normal piece of coax. There's no attenuation in this, okay? And by attenuation, we mean that the signal at one end of the cable is equal to the signal at the opposite end of the cable, okay? We're not reducing the voltage at all, okay? What you see is what you get. Now this here, if you can see that, is a proper oscilloscope probe. These are the ones that normally come in the kit when you purchase these, and when you purchase an oscilloscope or you're using an oscilloscope, you normally use one of these. This particular oscilloscope probe is a what we call a ×10 probe. At this end we've got our crocodile clip. Okay, this actually goes to ground. This is our ground connection. And at this end we can pull this back and we've got a hook. And that's what we do all our measuring with, okay? And if you want to do probing about, you don't want to use the hook, you can actually unscrew this, and you've got a nice little sharp probe here. Be careful with that one, because you can actually stab your hand on it if you're not too careful, okay? But always try and use the hook wherever you can, because you can hook that. If this is your wire that you want to measure, your signal, you can actually hook it on and you can take your hand away. It's not going to go anywhere, it's nice and secure. Okay, that's what we like about these probes, okay? You do secure measurements. Now these oscilloscope probes here, if you zoom in on this one, I don't know if you can see that, it's a ×10 probe. And now what we mean by ×10 is it has a ×10 attenuator. Now this one's ×10, so if we have 1 volt at this end, it actually gets attenuated by a factor of 10. You end up with 0.1 volt at this end. So you end up with 100 millivolts if you input 1 volt. Odd. Why would you want to do something like that? Well, oscilloscopes can only measure up to a certain limit. Okay, your graph will only go up to a certain amount. So if this was set to say 5 volts per division, okay, you got 5, 10, 15, 20, 25, 30, 35, 40 volts maximum that you can measure on this screen. 40 volts peak to peak. What happens if you're measuring 80 volts? Ooh. Well, if you have 80 volts, it will go off the screen. But if you use a ×10 probe, these amazing things, okay, you have 80 volts at this end, you'll end up with 8 volts at this end, okay, and it'll be nice and consistent. It'll be a consistent value, consistent attenuation, okay. So our 8 volts will be displayed, okay, so you will be able to see our 8 volts. But instead of you having to perform that mathematics, okay, that multiplication, that division, we have here a probe setting called probe voltage 10x. Now this is saying that it's expecting you to use a ×10 probe. So if you plug in a ×10 probe, you don't need to do any of that multiplication or anything. That's actually done internal in the unit. Okay. If it was a trusty BNC cable, this thing here, okay, without any attenuation, you would have to go into this menu. So all this menu is driven by the buttons next to the menu. So you go into the menu and you say, I want a voltage probe of 20, nope. 50, no. 100, no. 500, no. 1000, no. 1, X1. So if you was using a BNC cable like this one, you change this to X1 and go back, and we have a probe value of ×1. 1 times anything is 1. Well, 1 times itself is itself. You got 1 volt at this end, you get 1 volt at this end. You got 1 volt going in, it's going to multiply by 1, you get 1 volt displayed on the screen. Okay. Now, if this was set to ×10 and you used one of these BNC probes, what would you see on the screen? Well, you'd have 1 volt at this end, you'd have 1 volt at this end, but because this is set to ×10, it would actually multiply it by 10. So the value that you're reading would be 10 times bigger than what you was actually inputting into the oscilloscope. Okay, So you must pay attention to your probe settings. Moving on, I have another probe to show you. Okay, these are ones which are most common in the toolkits. Okay, you may get the ×10, you may get this one here. Okay, now these are a little bit more special probes. Okay, if you read on the probe here, okay, it's either X10 or it can be an X1. Okay, now what does that mean? Well, if you have, again, 1 volt at that end and the little switch on the side, if you switch that to X1, if you have 1 volt here, you get 1 volt at the end. Little switch on the side, if you switch it to X10, okay, this little switch here, if you switch it to X10, okay, if you have 1 volt here, you get 0.1 volts here. So this probe, okay, is a bit like having 2 of these. So you have a X1 and an X10 all in one handy tool, which is why most of the toolkits contain these, because you can use them both. Okay, so that is about probes, and that's why probe setting is there, and that's why it's very important. Okay, now then, measuring on your digital oscilloscope. Exactly the same way as on the analog one. The only difference is that the buttons and your values are slightly in a slightly different place, so you just have to go looking for numbers, essentially. So we'll plug in our signal into channel 1. Channel 1 is on. It says channel 1 here. It's currently 0 because it is grounded. It's around the centre of the screen, so we'll switch it on to first stop DC. As you can see, there's our waveform. It's scrolling across the screen just as much as the analog one was before we triggered it. Now we can change the trigger level and we can move it around the centre of the waveform. There it is, nice and triggered. So you can see our trigger level here. We knew it was above the waveform, so we just have to twist the knob until it is in the waveform, and there we are. We have a nice stable waveform. It's still scrolling across the screen, but it's been synchronized to this spot, okay, where the waveform starts, where we've moved our horizontal position to our triggered position, and we can measure it in much the same way as before. It's 500 millivolts per division voltage, so 0.5 volts, that's 0.5, 1 volt, 1.5 volts, 2 volts peak to peak. And the same for time, 500 microseconds, you can work it out. Okay, so that's 1, 2, 3, 4, 5, 6 divisions, just like it was before. 500 microseconds is 0.5 milliseconds. It's exactly the same. So this works out to be around 333 millivolts, 333 hertz. Okay. There we go, job done. Very simple. Just like before, you've got your DC coupled to DC, it's showing you you've got a DC offset, it's below our 0 line, which is still up here. You can still see our arrow, channel 1, pointing to where 0 is, and it's shifting it down. And again, you can change coupling to AC coupled. In case of digital one, it doesn't shift the voltage trigger level with it. You have to just re-trigger. And there it is, AC waveform measured exactly the same way, voltage, time. It's got rid of the DC component, and all that you're measuring is the AC. There's all that you're displaying is the AC. Simple. Okay then, a few little extras. Well, it's exactly the same way for channel 2. At the moment channel 2 is off. If you want to switch on channel 2, there it is, channel 2 is here, and it's a nice blue line so you can actually tell the difference between channel 1 and channel 2. Now then, a few little extras which the analog scopes doesn't have, and this can actually measure your voltages directly. So what we can use is measure or cursor. We do measure one first. We switch on measure, we press the measure button, it changes our menu down the side here to the measure functions, and each button next to each one, it controls what we want to measure. So if we want to change it, this one, channel 1, is currently measuring none. Hit the button next to it. You can say the source, so channel 1, channel 2, the blue line, math, which is off, this middle one, I'll come to that later on. That's if you want to do any mathematical functions. But at the moment we're on channel 1, so we want to measure channel 1. And you can change the type, which is the next button down, corresponding to the next block. You can measure, say, the frequency, or you can measure the period, you can measure the mean, peak to peak, so on. So, like I said before, we measured this as being 2 volts peak to peak. It's in actual fact 2 volts peak to peak. Hit the back button. If you press back, it's actually stored it up here. This is peak to peak. It will continuously measure it. We can move down to the next one. We can change this one. We can say measure frequency on this one. Back. And as you can see, it's actually 340 Hertz now, which is correct. The one that I measured myself, or the one that is measuring. Got a discrepancy. Okay, so it's up to you which way you choose, but always use the same way of measuring throughout your experiment. If you start to measure manually, measure manually all the way through your experiment. If you want to use the measure function, then use the measure function to measure all the way through the experiment. Otherwise, if you have any error in your manual measurements and then you decide to start using auto measure, you can end up with a huge error between the two. For example, I measured it manually to be 333 Hertz when this is auto measuring it to 340 Hertz. If we take a look, you can actually see that's because when I manually measured it, I actually missed out a little division, a little subdivision. If I move this in closer, okay, you can actually see it doesn't cross the centre of these two divisions. Okay, it's just before, so my manual measurement was slightly off. So this one's more than likely a more accurate measurement than I actually manually measured, which is why I said earlier that always try and keep the largest waveforms possible on the screen. That takes care of the auto measure function, but unfortunately auto measure doesn't work as well as you would think it does. Now, on a Tektronix oscilloscope, okay, it only has a small amount of what's called memory depth. Memory depth is how much information the oscilloscope can store about the waveform on the screen. On some oscilloscopes, they can store megs, hundreds of megs, tens of megs, so forth of data. On the Tektronix ones, it can only store about 2.5k of data, the data points. So on here, your waveform, because it's a digital oscilloscope, this waveform is actually made out of lots and lots of data points, lots of dots, essentially, in order to replicate the line on the screen. Because of that, okay, the auto measure function can only measure what is actually displayed on the screen. So, for example, if volts per division goes off the screen, if we change our volts per division, the waveform is off the screen. Voltage is actually being measured at only 1.9 volts. Okay, 1.95 volts. So you have a error, and the greater the volts per division, okay, it's at 100 millivolts per division now, the waveform is completely off the screen. It's only being able to measure 1 volt, and it gives you a hint that it's got a problem because it's actually got a question mark next to the number. So if you're using the measure function, keep the voltage on the screen as big as it can go, okay, and you'll get a nice accurate number. The same can be said if it's a very small value. Okay, the smaller the
value, it will have trouble measuring this as well. So at the moment it's measuring it at 2.2 volts. A lot more accurate because it's actually on the screen, but it's definitely not 2 volts. It's actually out by 200 millivolts. It's quite a large value. Okay, large error. Same for time. If you don't have a period on the screen, usually it won't be able to measure the time whatsoever. Sometimes it can, sometimes it can't. It's because your start and stop of the waveform, okay, its cross points are actually off the screen. It's got nothing to reference any other measurement to. So it won't be able to measure frequency. Just like volts, if you have too much information on the screen, okay, your error slowly increases, and again, question mark, okay, that you can't read it. So always make sure that you've got a couple of cycles on the screen, and that you've got at least 1 or 2 cycles, and that the voltage is clearly displayable. Just like the analog oscilloscope, you can only measure what you can see. Digital oscilloscope, you can only measure yourself what you see on the screen, and therefore exactly the same for auto measure. You can only measure what you can see. If you can't see the signal, you won't be able to measure it. The scope won't be able to measure it. Simple. The other way of measuring is using cursors. So if you press the cursor button just below measure, okay, just like the measure, you've got type and you've got source. Source is channel 1 because we're plugged into channel 1, so you can change the type. We're measuring amplitude. At the moment the cursors are set. Just so happens that they're set at the top and bottom of the waveform. Usually they're not. If you want to measure your waveform, you select cursor 1 and this knob lights up, and you can move the top cursor to the top of the waveform, channel 2, cursor 2 I mean, not channel 2, and you can move the bottom cursor about the screen until it's at the bottom waveform. Okay, so just when it's on its edge of the waveform, and you got a measurement of cursor 1 of 1 volt. That's from your 0, the ground, wherever you put your ground, to the top of your waveform. Okay, 0 to plus, cursor 2, 0 to minus. So 1 volt positive, 1 volt negative. That's 2 volts here. Peak to peak. Very simple. And the same can be said for time as well. So cursor 1, set cursor 1. You can move your cursor so that it's at, I don't know, let's do it back here. So it just crosses the time just here, and where it's 0 on the 0, if it actually goes to that. Right. Okay, so it's at 0 crossing point, that cursor 2. So it starts at, on the screen here, it's 500 microseconds per division. Our first division is at where it crosses is 160 microseconds at minus 20 millivolts. That's very close to 0 where it's crossing. To the end of our sine wave over here, so sine wave here is at 3.12 milliseconds at 0 crossing point. Difference between the two, 2.96 milliseconds, very close to our 3 milliseconds when we counted the divisions. Okay, but it's actually off by about a very, very small amount. Okay, points of a millisecond. Not points of a millisecond, points of a second. Yeah, points of a millisecond. Points of a second, same thing. Right. And it will give us a period. Below that, it also gives us 1 over the period, which is our frequency. So it actually tells you our frequency as well as our time. And the difference between the two cross points, you know, where it's crossing the axes, is about 20 to 40 millivolts. Now, in all these measurements, these auto measurements and cursor measurements, you will always see a fluctuation. Okay, so you may want to write down the minimums and maximums, what it's fluctuating around, and these will contribute towards your error in your reading. And you might want to note down, maybe as a percentage or plus or minus so many values, what this is actually oscillating around. Okay, so when you plot, if you have to plot any graphs, you can actually add error bars onto your graphs. So if you get any slight deviation between the points of your graph, your trend line should go through those error bars. So forth. I believe we might talk about error bars when we go through your lab books at some point, or we can shout out during the sessions or tutorial sessions about what the hell are error bars and how to use them and how to calculate them and so forth. But we'll come to that later on. Suffice to say, for an oscilloscope reading, it is an error. It is fluctuating. And that is your oscilloscope. So you covered how to measure using the auto measure, how to measure using the cursors, and how to measure using the screen. Okay, and then final thing about the oscilloscope, where we covered all the basics. Okay, how to measure time, how to measure voltage, so on and so forth, how to set it up. Just one more thing that I would like to go through. I'm not going to spend too much time on this because you don't really need to. And just once you get the basics and grounded in the scope, you don't need to really go into depth about this. And what I'm going to talk about is the math menu on digital oscilloscopes. Now, the math menu is full of mathematical operations, so what you can apply to channel 1, channel 2, or the combination of the two. Now you can do subtraction, multiplication, addition, but what I'm interested in is this function, the FFT, the fast Fourier transform. Okay, so what we've done is we've effectively converted our digital oscilloscope into a spectrum analyzer as such. Okay, it's not a true spectrum analyzer because it's performing a fast Fourier transform on the time domain. So what we've got on the screen when you run an FFT under the math menu is you now have a magnitude, okay, and you have a frequency. Okay, this is no longer time, this is actually frequency, and this is magnitude, and the magnitude is measured in dBs. Okay, decibels. Seconds per division knob now controls the frequency, and volts per division is actually measuring magnitude in dBs. So at the moment I'm feeding in a signal of 2 volts peak to peak at 1 kilohertz. At the moment this is set to 25 kilohertz per division. The centre of the screen is at 125 kilohertz. Well, that's miles above 1 kilohertz. But what you can see is just downside the screen, you can just see a spike downside the screen. This is where the 1 kilohertz signal is. Okay? And in order to change this 25 kilohertz per division, okay, we need to adjust it so it's, you're measuring in kilohertz and hertz, maybe hertz per division, because it's in kilohertz. 1 kilohertz, if you do 1 kilohertz per division, you'd see a spike at 1 kilohertz just here at the 1 division, but we've got the entire screen, so you might as well use the entire screen. So let's change that to a more suitable value, and as you can see, as I'm changing the scale, you can start to see our 1 kilohertz signal slowly creeping across the screen. So at 500 kilohertz per division, at 500 hertz, 1 kilohertz, and there is our 1 kilohertz signal. Okay, so we're actually looking at the frequency domain. So we've got frequency and magnitude. We've got 10 dBs at the moment is what the magnitude is set to, and you can use cursors. Source, you want to change it to math because we're in math, and you can change the type of measurement to magnitude or frequency. So frequency, you can move the cursor to this one to our peak, and we've got a frequency of cursor 1 is 1 kilohertz, and our magnitude is minus 3.39 dBs. Simple, done. Obviously, this is in dBs. Complete pain in the arse, you'll have to convert to volts. Okay, but not only can we measure frequency, you can also measure magnitude, so you can change your cursor so you can actually measure the magnitude. Okay, so you can place the cursor around the top of the peak, and there we go, 3.39 dBs of magnitude. Okay, and that is simply using the FFT. Now you measure off this screen exactly the same way as we did for the others. You're just counting divisions. That's all that you do. So I don't really need to go into depth about this because it's pretty straightforward. Once you know how to measure from the screen, you know where your divisions are displayed. It's quite simply just to let's just measure it straight off. And just for your reference, okay, 0 dB equals what? 1 volt. Okay, just remember that. Okay, and then you can do your conversion. See if you can do a conversion. Okay, at the moment it's minus 3.39 dBs, and you want to get to signal. If we go back to channel 1, reset this up so you can see some cycles. Okay, 2 volt is equal to 2 volts peak to peak. Job done. And that's the oscilloscope. Quite a lot for you to think about, quite a lot to digest. I suggest that you go through this video a couple of times, maybe at least twice. Okay, take a few notes. If you've got any points that you want to raise, just come into the lab, knock on the door, ask away. And don't be afraid of actually sitting down in the lab and pulling one of these off the shelf and taking a look at it yourself. Okay, it's all very well and good watching videos, but you learn a hell of a lot more when you start to get down and dirty and using these machines. And that's it. Oscilloscope off, and we are done for this tutorial.